Good evening to all the participants. On behalf of our New Horizon College of Engineering as well as the Department of Electrical and Electronics Engineering, a warm welcome to the participants as well as the today resource person, Dr. Rahul Sharma K, Attitude and Orbit Control System Engineer from Spacecraft Design Group R&D Division from Axel Space Corporation, Japan. Okay, this program will be hosted by the New Horizon Department of New Horizon College of Engineering. I'm very happy to introduce our today's speaker for this webinar program. Dr. Rahul Sharma completed his BE from College of Engineering, University College of Engineering, Todupuzha, Kerala, and received MTech in Embedded Systems from Amrita University, Coimbatore, in the area of cooperative path planning and mapping of sensor-based multi-robots for area exploration in unknown environment, and then received his PhD from robotics and control domain from University of Paris, Republic, and then joined as a professional, started his professional career at Nesma has owner Saudi Arabia as an electrical and instrumentation engineer, and then completed his PhD postdoc from University of Patrick and assistant professor at Amrita University, Coimbatore from 2017 to 2018, and then currently he is working as a R&D at Attitude and Orbit Control Engineer at Axel Space Corporation, Tokyo. Really warm welcome, sir. I welcome you for this international webinar program. With your busy schedule, you have accepted my invitation and joined the program. Okay, now we can start sharing the slides and you can start the session, sir.
Hello, I can hear me, right?
Yes, sir. Yes, sir.
Okay. So thank you, Vinod, sir, for inviting me for this webinar. So myself, Rahul Sharma. So I'm right now in Tokyo, Japan. So I'm working as Attitude and Orbit Control System Engineer in a company called Axel Space. So in this webinar, I'll be mostly talking about very basics of satellites in general and the space industry. And if you have some time, I also would share some idea about robotics and how can you build a career in robotics. Okay. So yeah, I'm going to start, and if you have any questions or comments or doubts, please you can feel free to ask me anytime. Okay. Yeah, so I might spend maybe between 30 to 45 minutes and the rest 15 minutes let's have a chat. Okay, so I would like you to be interactive, so you can ask me anything, and let's have an interactive section. Okay. Yeah, so as Vinod sir already explained, I'm going to skip. Okay, so those who don't know Czech Republic, I have some interesting pictures. Yeah, so this was my professor. He visited us once in Kerala, and we took him to the Toddy shop, and this is a picture from there. And yeah, this is in front of my university. And yeah, these are some of my friends. And this is my PhD thesis defense. And yeah, he's so funny, my supervisor. He photoshopped himself with his family. And actually, this photo was taken from Kerala, wearing, this lungi. Okay. Okay, now, yeah, from 2019, I'm working in a company called Axel Space. So, little bit about the company. So, Axel Space is a space startup company. Startup, even though it's 12-year-old already, but we call it a startup. Because we have only around 80 employees, and yeah, this is our team. Out of this 80, there are like 30 foreigners and from 18 different countries. So I'm the only one Indian right now in my company, and yeah, we have really talented young people Okay, so about my company. So my company, our main business is development of satellite. So we develop the satellite from scratch, and we sometimes develop for others. For example, this Rapids one, it's for JAXA, Japanese Space Exploration government organization, just like NASA in Japan. Also, we for private companies also, for example, WNI SAT is for space, not space, it's a weather news. This is private organization. We build for them also. And all others, this GRUS, WNI SAT, for these are our own satellites. And yeah, all these satellites are orbit right now. And this GRUS 1 BCD is part of a GRUS 1 constellation, which will be launched in next March. So the main idea right now is we are planning to have a constellation of satellites. So more than 5 satellites in one orbit plane, so that we can capture every part of the Earth with a reset time of 1 day, which means every day you can capture anywhere in the world. I mean, anywhere on Earth. Okay, so maybe let me. Okay, if you are interested, you can go to the our company website. So here you can find all the information about our company, and in career page you can also find the career opportunities also. Maybe I can play you a short video. It's a bit long video. Let me pause it. You can find from our gallery, you can find the pictures taken from our satellites. So these are the pictures. Some pictures are taken from our satellites. Okay. And our right now we have something called Axel Globe. Axel Globe is a platform where you can mention the place where you want to take picture, and our company would take pictures and would sell it for a small amount of money. Also, we also do some image processing, like analysis. So there are several applications for the images. For example, you can use it for agriculture purpose, or urban management, disaster management. There are several applications of these images. Okay, so let's get back to the slides. Okay, so yeah. So some of you already know a little bit about orbits and something to do with space. And I'm sure all of you might be knowing this about orbits. So orbit can be in, there are different types of orbits. For example, classification based on inclination. Here we have equatorial orbit, polar orbit, or inclined orbit. By shape, circular or elliptical orbit. By altitude, so we have low Earth orbit, medium Earth orbit, and geostationary geo orbit. So yeah, so let me briefly talk about the different altitude regions. So from Earth, we have a high Earth orbit where our geosynchronous satellites orbit, which is around 36,000 kilometers altitude. And all our GPS sensors are around 20,000 kilometers. And yeah, so in LEO zone or low Earth orbit, most of the satellites, especially for Earth observation or taking pictures of Earth, most of the satellite would be in this region. And you see, International Space Station is at around 340 kilometers. Our satellites lie in this region mostly, around between 500 and 600 kilometers. Maybe this could be a little bit boring for you, so I would quickly go through it. So when a satellite orbit or any object in space, we need to find, for example, we need to determine the geometry of the orbit, or we need to find the position of that object. So with these 5 parameters, you can calculate the geometry, and with these 2 information, epoch time and true anomaly, we can find the position of the satellite. So this is very important to us because this depends, this will decide all our mission and other things. Yeah. So semi-major axis, eccentricity, inclination, RAN, argument of perigee, epoch time, and true anomaly. So how to find an object or a satellite on space or in orbit? So every object orbiting around Earth will have something called the two-line element. So two-line element basically contains all the Keplerian parameters with satellite numbers and epoch time also. So there is an organization called the NORAD, North American organization. So they track all the objects orbiting the Earth, and they update it on daily basis, I think 3 times a day. So not only satellite, even debris also will have a TLE. Yeah, so if we go there, we can find all the information about any satellites or debris. Okay, so about today's talk. We plan to talk about low Earth orbit satellites, right? So you might be wondering what is satellites used for? So mainly we classify satellites based on mission. Earth observation means imaging the parts of Earth. Also technology demonstration, like for you want to measure something more remote sensing. For example, you want to see the global warming effect or something, or could be communication. There are some satellites right now which aim to provide internet, and also could be military. So based on mass, the satellites can be large, medium, small, mini, micro, nano, or pico. Our satellites mostly fall here between small, mini, and micro, so between 500 and 10 kilograms. We have satellites, I think maximum was around 200 kilograms, and we also have satellite with 10 kilograms. Okay, so Earth observation satellite. So there are basically 2 important terminologies which are commonly used. One is called SWAP, the other one is called GST. GST basically means the resolution on Earth. For example, our satellite Bruce 1A has a GST 2.5 meter, which means 1 pixel is 2.5 meter. With 2.5 meter pixel or a GST, we can identify a car from car. Identifying a human being would be a bit hard, but like for example, a car can be easily identified from the images taken by Bruce 1A. Also, the swath. Swath basically means the width of the image. So when satellite passes through an orbit, there will be something called nadir point. Nadir point is basically means the point just below the satellites falling on Earth. And the satellites can be rotated. So by rotation, we can take pictures not only at nadir point, or also we can have off nadir angles, for example, 30 degrees or 45 degrees. So we can also take pictures, for example, this side from this pass. We generally call pass. So there will be satellite will be passing through, let's say, in this pass. We can also rotate the satellite and take pictures from this area also. And the swath remains always same. Okay, so here it shows a list of all the satellites, GST from 100. So there are also now satellites with a GST of 0.5 or 50 centimeter, and the swath also. Okay. Okay. So now let me talk about my job, and maybe this might be more related to electric and electronics and what you are studying. So I'm sure you might have heard about attitude, or at least roll pitch angles, Euler angles. You might have heard, right? So basically, as I explained earlier, when the satellite passes, maybe we need to point the satellite to one particular area. So we need to rotate the satellite, right? So that's what attitude control does. Okay, so what are the main attitude types of attitude control we normally do on satellites? The first one is called the detumbling. Detumbling basically means when the satellite is separated from the launch vehicle, the satellite would be tumbling. Tumbling basically means rotating in all the three axes. So we need to reduce that angular rate or velocity of the satellite so that we can start our mission. So that detumbling is basically means reducing the angular rate, and that is normally done by something called magnetic torquers and magnetometers. I would explain a bit more in coming slides. Okay, so basically when a satellite is separated for the first time, first few days or weeks we call uh, operation time, and that also depends upon the satellite mission and various other things. So first step is detumbling, and this is extremely important. And next one is sun pointing. As you can imagine, every satellite will have some solar panels to generate electricity, right? So these solar panels, we sometimes we need to point to the sun so that we can harness maximum solar energy and generate electricity. So that is also a part of attitude control. Next one, as I explained earlier, nadir pointing. Nadir pointing means pointing at particular um, latitude and longitude on Earth, and sometimes we also might need to do off nadir. So we have some actuators, and we give commands to the actuators, and actuators would uh, there will be a closed loop feedback control, and yeah, satellite would be able to locate or point at particular location. So this one is normally used for image capture. And the third one, ground station tracking. So when we need to send some commands or get data normally data could be two types of data. One is mission related data. So basically, for example, if the satellite's main mission is to capture images, that image data we have to downlink, and sometimes we need to send commands to the satellite. For example, at this particular point of time, rotate the satellite, or make the roll angle this much, pitch angle this much, etc. And also, we also might need the telemetry data. Telemetry data means all the information about the sensors and actuators. Okay, so in order to do that, we will have ground stations. So there are several ground stations, uh, mostly operated by companies. For example, we normally used ground stations in Norway, and when the satellite passes uh, over the uh, over that particular ground station, we might need to uh, track that particular point. So that is also attitude control. So here we have to track a particular point. So this is a bit different from another pointing, but comes under attitude control. Okay, so now I guess you might have already got some idea about attitude control. Maybe I would also bit talk about attitude. How would we represent attitude? So as I explained earlier, you might have heard about Euler angles, right? Roll, Piccio, and Euler angle representation. We normally use something called quaternions. I'm not sure you might have heard about quaternions, but basically quaternions are a mathematical representation for three-axis control, which is a how would I say? Which is an extension of the number. Okay, so these quaternions are not only used in space industry, but it's also used in, for example, in video games or in yeah, drones. Basically, when we have a 3D rotations, nowadays quaternions are mostly used because Euler angle representation has some drawbacks. I'm not sure you heard about the gimbal lock. So that can be avoided if you use a quaternion representation. Besides that, I explained you roll PTO, right? But we need to have a reference frame. So reference frame means, X, Y, Z axis, but where to keep and because the satellite is rotating around the Earth, right? So where can be the reference frame? So it can, there are also various representation. For example, there is something called the ECEF or inertial frame, which means uh, the origin of the reference is there, and then X, Y, Z axis are in particular represented in particular format, and also there could be body frame. There are several frames. So we normally work with the different frames and different types of quaternions. And the quaternions could be also depending upon different frames. Okay. Okay. So let's talk about orbit control, my second part of my job. So as I explained earlier, all the satellites in a particular altitude, right? But uh, sometimes we need to change the altitude. Firstly, mainly because there will be something called altitude decay, which would happen because of the disturbances. There are several disturbances. For example, there could be atmospheric drag or solar radiation pressure. There are several disturbances which can affect the satellite's altitude to be reduced. So sometimes for mission requirements, we might need to bring it back to the original altitude. So we need to have some sort of a mechanism to do that. Besides also, for example, collision avoidance. When we find that there is a chance of collision, we might need to change the altitude. So for altitude or orbit control, we use thrusters. I'll explain about thrusters later. And the most common strategy for orbit control is something called Hoffman transfer. Hoffman transfer is basically you will have two kicks, one at apogee and one at perigee. For example, here. we give one kick so that from the circular orbit, the satellite will be orbiting in elliptical orbit, and here next at the VDG, we'll have uh, another kick or another thrusting to make it to circular orbit. So from this circular orbit to this circular orbit, or from this altitude to this altitude, we normally do two times burning or kicks or thrusting. Okay, so there is a free simulator available from NASA. It's called GMAT. Maybe I can, let me see, I have. Yeah, so you can download this GMAT for free. And the syntax is quite like MATLAB, and also it also have, you can also use a GUI. Okay, and graphically you can simulate these things with this GMAT tool. So if you are interested, please download this software and explore. Okay, so it's called GMAT, General Mission Analysis Tool from NASA. Okay, I think 2020 version is also available. Yeah, next about CubeSats. So CubeSats are a satellite like represented cubes. So one U or one cube is 10 centimeter cross 10 centimeter cross 10 centimeter. So this is something nowadays become a standardized way of representing satellites. So you can have like 6U or 12U, and not only industry but academia, most of the universities around the world, students are developing satellites and trying various things. So even one U can have all the sensors and actuators in one single cube. Okay, so basically main components: antenna will be there for communication, solar panels for power generation. This is electrical power system board, and there is communication module. There is onboard computer and ADCS or attitude determination control system, and payload. Okay, so now let's talk about the most commonly used sensors and actuators. Okay, so I explained about attitude control, right? But before controlling, we need to determine or estimate the attitude of the satellite, right? So there are several sensors, basically 1, 2, 3, 4, 5. Most commonly used 5 sensors. We use in redundant configuration or complementary also. For example, sun sensor. Sun sensor is a sensor which senses or detect the sun vector or let's say position of sun. Then there is star tracker. Star tracker basically is a small camera, and this star tracker takes images of the sky or space, and it will have it will detect the stars, and it will have something like a map of all the satellites, and with those two information it would output the attitude information. And then magnetometer, which basically means measure the Earth's magnetic field, Gyro, I'm sure you all know about gyro. Basically, it would give you angular rate. From the angular rate, we can find the roll PTO. GPS sensor to dictate the latitude and longitude of the satellite, as well as GPS sensors are used for time synchronization. And reaction wheel. Reaction wheel is an actuator. Reaction wheel, to put it simple, it's a DC motor with a rotating disc. So basically, this works in the principle of Newton's third law, which means reaction. So when the disc rotates, or let's say the motor is rotating clockwise direction, then in anti-clockwise direction there will be reaction torque generated to conserve the angular momentum. Okay, so we'll have multiple reaction wheels, and then magnetic torques. I explained to you about detumbling, right? So during detumbling, we use a combination of magnetometer and magnetic torque. Basically means magnetometer would measure the Earth's magnetic field, and magnetic torque would be actuated so that there will be magnetic moment generated, and with that there will be torque, and we can control the angular rate of the satellite. And next is thrusters. Thrusters are normally used for altitude, not only altitude, but also we can also control the inclination of the orbit or RAN. And basically means we can adjust the orbit of the satellite. So there are several kinds of thrusters available. The most common or simplest one is something called cold thrusters. Cold thruster means most of the cases there will be nitrogen gas. So the nitrogen gas will be from the nozzle will be exhausted, and also similar to the reaction force, the satellite would be thrusted. So there are also other kinds of thrusters like chemical or ion engine or electrical. There are several kinds of thrusters. Okay, so that's all with different kinds of sensors. So we use multiple, not just one sensor, but a combination of the sensors to determine the attitude. Because most of the mission requires a really precise control of altitude, like the error could be within 0.1 degrees. Can you imagine 0.1 degrees, right? So we need the attitude determination accuracy also pretty good. So we basically use multiple sensors, or multiple means not only one, but the same sensor with other sensor, something like sensor fusion. And we can use a Kalman filter to get a precise, not precise, but much more better determination or estimation of altitude. Also, reaction wheel, we use multiple reaction wheels, not only for redundancy, like if one reaction wheel fails, but for other reasons also, magnetic torques also. Okay, so that's it with the sensors and actuators. Can I go to the next slide? Okay, so now let me quickly talk about the different space startup companies. So there are classification based upon, we fall under this category, like satellite constellation operation. So there are some big players like Planet, SatLogic, OneWeb, and Axel Space is here. Yeah. And spacecraft design and launch providers. So Spaceflight, Blue Origin, SpaceX, they are the main launch providers. Okay, now a little bit about the satellite industry. So these are the number of satellites launched per year. You can see that it's increasing year by year. And in 2019, there were 490 satellites being launched. And these are the applications. So most of the satellites were launched for telecommunication purpose, 29% for technology, Earth observation, 17%. Also, most of the satellites are out of 490, 438 were for a low Earth orbit. Also, sun synchronous orbit. Okay, so this is the future of the satellite industry. So it's predicted that the number of satellites would be 4.3 times more. And by average, every year, there will be 990 satellites launched. And there, according to this prediction, there will be 20 different types of constellation. And ours also included here. Yeah, so that's all with space and satellites. So if you have any questions, please, let's have an interactive section. Yeah,
Yes.
it was boring for you, or it was interesting? I don't know, maybe it's too complicated. I'm not sure.
Sir, actually, one of the participants raised a question. Which
Yes.
Earth orbit is suitable for satellites, and why such particular orbits for particular launching?
So the question is, which orbit is
Which
useful for?
is suitable for satellites, and why such
Mhm.
particular orbit or particular launching?
Okay, so this all comes to there are several things to be considered, but the most important one is the mission. So if the mission is for Earth observation, then most of the satellites would be something called sun synchronous orbit. And if the mission is a little bit different, like technology demonstration or remote sensing, it can be in different types of orbit. Like most of the sun synchronous orbits are inclined, but it could be also equatorial, or if it's for a communication, it can be different. So it all comes down to the mission, mainly mission. And the altitude, height also, not only the orbit plane, but the altitude also comes, it depends on the mission, type of mission. Did I answer your question?
Yes, yes. Another question. Second question. Why star tracker is used here?
Okay, so out of all these sensors, okay, you can use sun sensor, gyro, and okay, combination of sun sensor and gyro, you can estimate the orientation or altitude of the satellite, but it's not that accurate. There are several, for example, there are several issues with the gyro noise and angular random walk. There are several things, also sun sensor also. So these two are not so accurate, but star trackers are the most accurate among all other sensors. So we mostly use combination, but this star tracker is very important if you want not fine attitude control. If you want coarse attitude control, like we don't really care about if it's allowed to have like a 1 degree or 2 degree of error, then it's fine. We can use sun sensor and gyro. But if you need like 0.1 degrees, within 0.1 degrees, then we have to use star tracker. It's so accurate.
Another question. Orbital perturbations will be more for low Earth satellites.
Yes.
Okay.
It is.
Okay. How you and your team handle these challenges?
Okay. So the main, okay, For attitude control, we have the sensors, right? So we have the combination of sensors and actuators to handle all the disturbances. For altitude, we use orbit control, we use thrusters. But the thrusters, we don't use it often. We make the corrections once in, let's say, 3 months or 6 months. But altitude control, we do it most of the time.
Okay.
Or attitude control, sorry.
Okay. So next question, how do thruster work? Is it similar to aircraft? Thruster.
Aircraft, yes. Okay, so aircraft thrusters, if you are talking about the propellant, like this drone propellant, no, but the other propellants, and not how would I say that? Something like you have a high velocity gas is uh, being how would I say, exhausted out of the nozzle. Yes, that with that thrust, we can uh, increase the velocity, orbital velocity, and the velocity increases, the altitude also changes, increases or decreases.
Okay. Another question. What is the difference in the work of magnetometer and thruster?
Magnetometer is a sensor. Sorry, between magnetometer and
Say, thruster.
magnetometer is just a sensor which measures the magnetic field, the Earth magnetic field, and with three axes. All these are three axes. So X, Y, Z axis, it measures the Earth's magnetic field, and thruster is entirely for different purpose. It is for example, it can be for altitude control. If we want to increase the height of the satellite by 1 kilometer, or you want to change the inclination by, let's say, zero point 0.1 degrees, or you want to change the uh, L10, it's too complicated to explain. There is a Keplerian orbit called RAN. Sometimes we need to adjust that also.
Okay. Another question, can we launch a satellite in between two orbits of Earth? Let's suppose lower and middle orbit of Earth.
Yeah, we can launch anywhere we want.
Okay. Okay. Sir, what is the difference between very low orbit sat and,
Mhm.
low orbit satellite? And also, what are their applications?
You mean this Leo and high?
Yes.
Uh, okay, Leo zone. But when the satellite is closer to Earth, there are more atmospheric drag, and we need more thrusting, or we need to adjust. We need to do the corrections more frequent, and we need more fuel. But if it's far away from Earth, the atmospheric drag part is uh, too low. But if it's too high, for example, we have some satellite in 20 kilometers, we cannot capture the images on Earth.
Okay. Uh,
So basically, higher you can see that most of the uh, high Earth orbit or above medium Earth orbit, you wouldn't normally see Earth observation satellites, but for communication or other purpose like GPS.
okay. Another question, whether old satellites are using or
Oh,
reused, whether old satellites parts are reused.
uh, okay. So okay. So this comes to the question that what happens to the satellite when the mission is over?
Yes, yes.
So most of the satellites have a design lifetime. For example, our satellites have design lifetime of 5 years. So after 5 years, what happens to the satellite, right?
Yes.
Okay, so that's very interesting. So we cannot reuse the satellite. We have to. Okay, so what happens is that the satellite would be burned itself. For example, let's say our satellite is at 500 kilometers. If we are not doing anything to the satellite, like we stop all the control of the satellite, it because of the various disturbances, it would come closer to the Earth, and at around 200 or 100 kilometers, it would start burning itself, and it would be damaged. So nothing would come to the Earth.
Okay. What is the basic difference between uh, Gyro and GPS?
Gyro,
And GPS.
gyro and GPS. Okay, so gyro is all gyro. Even your phone have gyro sensor, right? So gyro basically would give you the angular rate in three axes, like roll, pitch, and yaw axis. So that is used for attitude determination to find the posture or attitude. And GPS sensor is just like in your phone. It would give you main information like latitude, longitude, and real-time clock. So we use the latitude, longitude information as well as the real-time clock for time synchronization.
Another question: why satellite using technology are high in cost and not available for public?
So the satellites, you can imagine, right? We have all the sensors available, right? So what is the biggest problem with satellites? The main thing is that we cannot repair anything hardware, right? Once deployed to the orbit, we can just change the code or give different commands. That's all. So we need to put a lot of effort in R&D and to make sure that everything goes as planned. So I think that's the reason why there are. But nowadays, all the informations are available, and there are, for example, you can even get all the parts now. You can buy all the components as it is, and you can basically assemble everything. That's what the most of the academia are doing. Not exactly. For example, academia would be designing the payload, and they would buy something called codes. Codes means commercial off the shelf. So the codes products you can buy, and you can assemble everything and attach your payload.
Uh, okay. One more question:
Mhm.
America going to place soldier in space? Will it change future for space research organization? Any political influence?
Uh, I am I am not that much expertise. I don't have that much expertise in. I'm just like a normal engineer, and I like building technologies and work with sensors. So I am not that much expert in the space politics and other stuffs.
Okay.
Maybe not.
Okay. Another question. As we know, SpaceX is going to put more than 30,000 satellites in space.
Yes.
Will this not cause a space debris problem? And how will it further affect our environment?
Mm-hmm. So this debris, there is these are not really debris because these satellites are controlled and that would burn itself. Like, uh, okay, so as for now, there aren't that many regulations like what we should do with the satellite after our mission lifetime. But there are several. Some of the organization are planning to bring in some regulations like you have to destroy your satellite after your mission lifetime in 5 years or something. So I'm sure that this won't create that many problems. So with the debris, I don't think the satellite debris would be that much as a big issue. But you know this anti-satellite test which we conducted in India, and that created a lot of debris. So let's pray or hope that there won't be any more kind of demonstration going to happen in future, because that's the biggest issue. With the satellites, I don't think.
Okay. Another question. Till now, there is a huge development with satellites. When will the problems of safe debris will be solved? Comment on Indian poverty and the problems with Indian space mission.
Okay. So first question was about debris, right?
Yes.
So debris, I don't think so, because space is that big. You can imagine, right? There is Earth, and then there is that many space around us. So debris, I don't think so, because we already saw that, right? 990 satellites every year in that big area. So I don't think that would be that much of issue. About space industry in India. So I think there aren't much of startups in India. In Japan, it's pretty common. There are several space startups and companies working on. In India, mostly ISRO. But I heard that recently the government is promoting startups to come up and build their own satellites and work together with ISRO. So let's hope that there's going to be more startups.
Okay. That's all, sir. No more questions.
Mm-hmm. You can ask me anything related to space or about Japan.
So if you have any queries, please unmute your mic and you can speak to the resource person.
Yeah, let's talk. Come on.
Sir, can you just comment about the Indian poverty and other problems versus the Indian space mission? What problem must be solved at the time? Shall we go with solving the problems of poverty and other problems, common man problem, or with the
அந்த கூகுள் மீட்ல தான் ஏதோ பிளான் பண்றாங்க மேடம்.
Okay. So you are talking about do we need to spend more money with ISRO, or should we do something with poverty, right?
எடுக்கலீங்களா? சரிங்க மேடம். நான் அப்டேட் பண்றேன் மேடம். நான் இப்ப கேட்டுட்டு உங்களுக்கு லைன்ல வரேன். ஓகே.
The poverty will be not reduced or alleviated. How do you say that? Will be gone. But we need to be a technology leader also, like Japan. Japan has what Japan has. That they have some really hardworking people, and yeah. So I think we have to develop our technology, like for ISRO, or we should have more startups, and we should be technology leader. And with that, everything would be fine. We'll be economically better, and all the poverty and other things would be gone. That's my personal feeling.
Sir? So most of Indians are working in NASA and other space organizations like SpaceX. Why can't they come into India ISRO development center?
I think there are something like brain game. Brain game means a lot of Indians coming back to India. That's happening, and yeah, I think it's happening, and it's good, right, to get expertise from outside and come back and contribute to ISRO.
But India is lacking on that, sir. If America,
India is not lacking. ISRO is great, right? We are
not like that, sir. Means in some cases, like GPS has been around for America so long, but now only we launched Navic satellites, right?
Mhm, mhm.
In some areas we've been
Yeah,
lacking.
but we are still better, right? In my understanding, uh, maybe US, European Space Agency, JAXA, and now there is Chinese, and then India. Like India is like in top 5.
So I think that India is growing in terms of space because in ISRO, one record it is there that between very cheap and its performance is very high, and in very cheap cost they do the
Mhm.
correct high performance. So I think it's growing,
Yeah,
and it's not the problem; it's our success.
mhm. Yeah, I feel that we as like ISRO is a huge success, and they are doing really great things. So come on, you guys have to work hard and try to work for ISRO or some startups in India or outside, or yeah, try it. You all can do it. So in my case, I was not that kind of a big kind of studying kind of guy. So during BTech, I was not that into to the all subjects or something. I was really picky and I liked only few subjects. And yeah, but everything changed once I started working in Saudi Arabia. I felt I didn't study well. Maybe I should try it one more time. That's how I did my MTech. And MTech, I did my level best. I studied something for myself. Yeah, before I was also kind of lazy. Any other questions? So,
Any questions?
so let me. I have some slides which basically do with robotics, but I would like you to learn some tools. So I'm sure that you all are, have some exposure to C++ and Python. If not, please start as early as possible. And if you are interested in something with robotics or anything, please Arduino, Raspberry Pi, or Lego Milestone. And MATLAB and Simulink, it's used almost everywhere. And if you are more into robotics, go to Linux, and ROS is a robot operating system. And there are several simulators like Gazebo. And yeah, there are like Ardu Pilot Mission Planner is for drones, and Kerbal Space Program is for space. Yeah, so try we have try. You can learn yourself. There are a lot of materials available online. Try yourself. Yeah. Any other questions?
Sir, no more questions, sir.
Yeah, sorry, I didn't see any of the chats.
Yeah, any of the chats. Thank you, sir. Thank you for your valuable presentation and a very informative session, which will be relevant in the space industries. Okay, maybe it will be new to the student community as well as the faculties, because they won't get some of the informative session. Okay, but your session is very interesting and more informative, sir. Thank you, and accepted my invitation in your busy schedule. You have allocated the time, okay, within a short span of duration. Okay. Thank you. Thank you.
Yeah, and I must appreciate, like, I had given maybe 2, 3 webinars before, but it was never this interactive and this many really interesting questions. So yeah, congrats, you have really nice students. And yeah, please feel free to write me if you have anything. Rahul Sharma K14@gmail.com. So I will try to answer your queries. So good luck, and yeah, if you have anything, please write me by mail.
Yes, sir. Okay. Thank you, sir. Thank you. We'll wind up. Okay. Thank you, participants, for joining the today webinar program hosted by New Horizon College of Engineering. And the certificates I already posted the attendance and the feedback session about the speaker in the chat box. Please give your attendance and feedback relevant to the session. And the certificates will be dispatched to your registered mail IDs by a couple of days. That is by tomorrow you will get it. Before 5 p.m. Everybody will get the certificate. Okay. And the New Horizon College of Engineering, it is one of the autonomous institution which is situated in the heart of the city, electronic city, Bangalore. And our institution will be one of the oldest and reputed institution in Karnataka as well as India also. Okay. So the Department of EEE is organizing many programs in the upcoming days. So the details has to be shared to your mail IDs. Okay. So please keep on touch with us. Okay. Thank you. Thank you. Now I'm going to wind up the session. So please give your attendance. The link which is available in the chat box. Okay.